Hi there, I'm going to talk to you about hazards and hazard ratios to follow on from the presentation the other day where you learnt about risks and risk ratios and odds ratios. Didn't have time to look at hazards and hazard ratios, but this is hopefully going to cover that. So when you do a sort of standard categorical analysis, you often have a problem with dropouts. So let's just say you've got a follow-up point at, say, 5 years. If people actually drop out of the study before 5 years, and they haven't yet had an event, then you've pretty much lost that person. They may have had an event after dropping out before the follow-up point, but you'll never really know. So they're not actually counted in the analysis. Whereas the hazard approach that I'm going to go over with you now actually differs from that in that it does a little trick. It looks at the analysis in small intervals of time. So the analysis occurs sequentially over separate small slithers of time. And I'm going to show you this in a very concrete way in a couple of slides. And by doing that, it allows it to cope with data loss by using data until the moment it's lost and then adjusting for that loss. So if someone's data is lost at, say, 6 months during a 5-year study, you can still use that person's data until that moment of loss. And then you adjust for the fact that that person's gone from the analysis. You adjust the number at risk. But all this will become clear. Nice little quote here that sums up the advantage of the what we call the survival analysis method. So looking at hazards is called survival analysis, and it adjusts for the occurrence of censoring in each observation and thus is advantageous in that it uses all available information. Right, what we've got here is a life table. And this is a life table for just one of the groups. So let's just say that we're comparing paracetamol against aspirin. This might be the life table for the paracetamol group. We'll have another life table for the aspirin group. But I'm not showing you that to you now, keeping things simple. And you can see that we've got rows and columns here. Let's just look at the columns first. So in the first column, we've got intervals. And these are intervals of time. Now what you notice is that we haven't actually defined the lengths of time yet. And that's because they're defined by the point at which somebody either drops out or has an event. So the intervals have a time associated with them, but the end of the interval is defined by the point at which an event or censoring occurs. Now by censoring, I mean somebody dropping out. Anyway, the start of that first interval is of course at time 0. That's the only possible time that you could apply because that's the beginning of the study. Right, let's look at the time at the end of that interval. It just happens to be 15 days. Now that has been defined by the fact that if you look across that row, interval 1, you can see that one person was censored during that interval. In other words, one person dropped out. Nobody died, as you can see from the next column, but one person did drop out. And so that defines the point at which that interval ended, and therefore the point at which the next interval begins. So the intervals have times that are quite random, well, they appear random at first sight. They're not really random, they are defined by the point at which something occurs. So the next interval might be at 25 days. But let's stop there actually, and let's just go back to the columns. So the second column is the number at risk at the start of the interval. So you can see that for interval 1, we've got 30 people at risk. And that is really the number of people in that group at the start of the study. So you know that's the sort of number you might expect, 30 randomized to the paracetamol group, 30 randomized to the aspirin group. We're just looking at the paracetamol group here. We've got 30 people at the start of the interval. Now, if we go across that row, you can see that one person was censored. In other words, one person dropped out, but nobody died. So, and that of course must have happened at 15 days. And only one of those things happens to trigger the end of that interval, and therefore you can only have one. You can't have someone censored and somebody dying. So it's the first that occurs. So one person dropped out, and if you go along to the penultimate column, the proportion surviving that interval, it's actually still 100% because nobody actually died. Somebody just dropped out, but dropping out doesn't mean you didn't survive. So we still got 100%. And the cumulative survival at the start, well, that's still 100%. This is the first interval, so that's easy. Right, we go down to the second interval now. And if you look at the number at risk at the start of that second interval, you can see that there's 29 now, because we're taking account of the fact that somebody dropped out in the previous interval. So we've taken account of that dropout. Now this time, nobody drops out during this interval, but at 25 days, somebody dies. And so we now have a situation in that group where 29 began, 28 out of 29 survive because one dies. And 28 out of 29 is 96.6%. That's the proportion surviving that particular interval. The cumulative survival from the start is basically 96.6% of the people in that interval, which as a proportion of the people from the beginning would be 96.6% multiplied by 100%, because there are 100% of all of the people in the study going into this second interval, which of course is still 96.6%. Right, so let's go on to the next interval. So that starts at the end of the second interval, which was 25 days, and ends at 30 days, because at 30 days, again, you can see from this interval, somebody dies again. So you have 28 at risk at the start of this interval, because remember, somebody died in the previous interval, so there's now only 28 remaining at risk. Nobody was censored, but one died. So out of the 28, 27 out of the 28 survived, which is 96.4%. Now the cumulative survival is going to be 96.4% of the number who were present at the end of the last interval, which was 96.6%. So 96.4% of the 96.6% gives you 93.1%. So that's the cumulative survival. Right, we go down to the next interval now. I'm not going to go through all of these intervals, but this is quite an interesting interval. This one ends at 54 days, because at that point somebody is censored, somebody drops out. Now there's 27 at risk because somebody died in the previous interval. Nobody dies in this one, so the proportion surviving is 100%. And so the cumulative survival is 100% of the previous interval's cumulative survival of 93.1%, which is, of course, 93.1%. I think the really interesting thing about this interval is that it shows us that this person dropping out at 54 days was included in the overall analysis, was contributing to the data in the previous intervals until that moment. But if we look at the next interval, you can see that the number at risk is now down to 26. So we've adjusted for that. But the important thing is that that person who dropped out was in the analysis up to the end of interval 4, contributing to the data. So we had lost something by that person dropping out, but we hadn't lost as much as we would have done if we'd looked at it in the conventional way. So you can carry on through all the intervals in just the same way, with the interval time points defined by the moment at which an event occurs or censoring occurs. And the two columns that you need to pay attention to are the first one, the interval column, with the times, and the cumulative survival. Those are the two columns of importance that we're going to use in a graph on the next column. Now, people struggle with this concept of cumulative survival. So in that second interval, 96.6% of all the people who had actually gone into that interval, so that's 96.6% of actually 100% of everybody, because 100% of everybody went into that one because nobody had not survived previously. So you'd multiply it by that to get how many people are in that particular, how many survived up to that point from the start of the study. That's what it means by cumulative, from the start of the study. And then, of course, for the next interval, 96.4% of those 96.6% would give you 93.1%. And that's how it works. So it goes like that. Hopefully that's fairly clear, but I can explain that again if you like. I think just a period of quiet thinking with a blank piece of paper and doing some drawings will help you to understand that. So remember, we had two columns there. We had the times, and we also had the cumulative survival. So we can actually plot the cumulative survival on the y-axis, percent surviving, and the time on the x-axis. And then you can take the data from both of the life tables. So remember, we have two life tables, one for aspirin, one for paracetamol, or we can call them treated and control, and you can plot them together on the same graph. This is where the data come together. And this just visually tells you quite a lot. I mean, it tells you certainly that you'd rather be in the control group than the treated group. If you look at 100 days, you follow that up, you can see that about 75% have survived in the control group, but quite a few less have survived in the treated group. You can see that the plots have these sudden drops in survival, and of course that's the point at which people die. You can also see these little blips going vertically. That's actually to represent the point at which people were censored. And so you've got that, but really you want to do a bit more than that, and we want to actually work out the hazard ratio. So how do we do that? Well, first of all, you define an interval. You take any interval you like. Let's just say take an interval of 5 days. And let's look at the hazard in one of the groups. So let's look at the treated group first. So that's the blue line. And if we wanted to know the hazard during that particular interval, what that is defined as is the hazard in the treated group is the number dying during that interval divided by the number at risk at the start of that interval divided by the length of that interval, which is 5 days. Now, if you look at the quantity in brackets, you can see that that's actually just simply a risk. The number dying, the number with the event, divided by everybody in that group, which is simply a risk. So a hazard is actually a risk divided by the length of time that risk occurred, which is a rate. So a rate is a risk divided by time. And if we were to put numbers into this, let's just say 2 people in the treated group died during that small interval of 5 days, out of 25 at risk at the start of that interval, and then divided by the 5 days of the interval, you get a hazard of 0.016. And then you'd have the same equation for hazard in the control group, of course, which would be number dying divided by number at risk divided by the interval length. Let's just say this in this group only 1 died out of 32 people at risk at the start of that interval, then divided by the same time interval of 5 days, and you get 0.0625. And then the hazard ratio for that interval is simply the ratio of those two hazards, which is 2.56. Now that's just the hazard ratio for that interval. What we want to know is the overall hazard ratio across all the small intervals. And you'd simply do some kind of mathematical pooling, not unlike the kind of pooling that you do in a meta-analysis, to be honest. But actually, the overall hazard ratio shouldn't be that different to the hazard ratio in any particular interval, because one of the assumptions of doing this kind of analysis is that the hazard ratio doesn't really change too much over time. I think it's called the proportional hazards assumption. It's quite an important assumption, but I won't go into that too much. So the hazard ratio overall is simply the pooling of all the separate hazard ratios within all the separate individual small intervals of time. Remember, within those small individual slithers of time, that allows you to take account of people who are censored. It allows you to use their information up until that point of censoring, so that's really good. And you can see also that the hazards are actually a very simple concept. It's just simply a risk divided by time, specific to that particular small interval of time. So that really is what hazard ratios are. There's no real mystery to them. And that's a good link to click on if you want to know a bit more. In terms of wanting to be able to sort of define what a hazard is, or to interpret a hazard when you see it in the paper, say you saw a hazard ratio of 2 for the outcome of mortality when you're comparing A versus B. What that means is, at any point in the trial period, a person taking drug A who has not yet died, so they're still at risk, has twice the likelihood of dying by the end of the next time point compared to a person taking drug B. And that really is all it is. So you can see it's similar to a risk, but it's a lot more than that. It's a lot more complicated, and it's a lot more flexible and allows you to cope with censoring much, much better. Now, one thing to say before we finish, though, is that when you're doing a meta-analysis, and some studies have hazard ratios for an outcome, and others have risk ratios or odds ratios, you can't mix them up. You certainly can't put risk ratios with odds ratios, and equally you can't put hazard ratios with either of those either. So you have to do a separate analysis for the studies looking at hazard ratios, and you can't convert them either. It's very difficult to do that. And the other thing is that a hazard ratio will always be given as the hazard ratio and its 95 confidence intervals in that particular study. There's rarely a way in which you could use the raw data to input to RevMan. RevMan won't calculate hazard ratios based on raw data. It does that for mean differences. So you just put in the mean in each group and the standard deviations and the numbers, and then it will work out the mean difference with the 95% confidence intervals. But it cannot do that for hazard ratios. So you have to use generic inverse variance to input the full measure of effect. So you choose the option when you're setting things up as generic inverse variance. And that will give you a nice generic inverse variance forest plot like this. So you probably use the calculator function to input the data on RevMan. You put in the hazard ratio and the standard error, and you go from there. Very importantly, you've got to use the log of the hazard ratio. So you'd have to make sure you put your hazard ratio in the right box. It may look as though it's very easy to put things in the wrong box there. So be careful with that. I think you just need to practice that really. Okay, thank you. Hopefully that will answer most of your questions. Any other questions? Please send me an email. Thank you.